demo, the magic that we can do with Kubevirt. In the slide, you can see that there is a list of things that we want to show. I decided to adapt the whole deployment to something that is usable by everyone. So I'm going to start to show initially what is the creation of the stack via Terraform. I use the Kubevirt provider. So basically this is available in a repository that will be included in the comment section. And you will see that you can do the same thing with your machine at home. You just need some resources. We will see how many memory and CPU I'm using, but you can really scale down to your needs. This repository is available on GitHub. You can just check it and do the experiments at home. Let's start just enumerating the content of the components that are created by this stack. You see that here I'm using the Kubevirt provider for Terraform. So in the README file, following the instructions, you will just have to init, create the stack, and when you finish, you can destroy it. And you will need a virtual machine manager on a Linux operating system, so running QEMU and KVM that are pre-requirements for this. I am using 16 gigabytes of RAM for each node. I am creating 3 masters of an RKE2 Rancher cluster, and in this case, 2 agents with, again, 16 gigabytes. So if you do the count, you will need more or less 64 gigabytes of RAM available on your machine. You can also scale down these resources. For cores, I'm using 2 cores for each of the virtual machines that we create. And once you apply this, basically the fast and brief result will be that in your virtual machine manager, if using it, or virtual shell, whatever other QEMU KVM manager you decide to use locally, you will have a 5-node RKE2 cluster available for deploying whatever you want on top of that. In the Terraform stack, there are cloud init files that are already providing you the ability of having a pre-configured machine. The password that I used for accessing the nodes is Ubuntu, so it's written here in the comments. It's very straightforward, and it's already installing RKE2 for each node via the cloud config. I'm using the Ubuntu Cloud Image base as the operating system for running Kubevirt. On top of that, I'm installing the latest version of Kubevirt, and it's everything straightforward. So you don't have to bother about looking at how it's done from the perspective of installing the manifest files inside Kubernetes, but you can go and look at how it works generally on your machine and then go digging in how it's done later. That is generally the limitation that now is available as a breaking point on the internet. So if you start following tutorials, you will not have all the straightforward process. Saying that, on the Terraform deployment, at the end, you will have this 5 nodes cluster that is basically already a virtualization. What I wanted to show you here is that you can have nested virtualization. What we are running inside these clusters are real virtual machines by QEMU KVM, produced and managed by Kubevirt, creating some custom resource definitions. But in a real case scenario, a production one, these should be bare metal instances. Or if you want to purchase on the cloud something like bare metal servers on your favorite cloud provider, it will be not that cheap as having something that is running on native bare metal, but you can do basically the same stack provisioning and getting the same results for your applications and similar. I've been using as a source of our future virtual machines that we are going to see here for creating the Ubuntu one, the classic process that you do for QEMU KVM. So starting from the virtual machine manager, using a specific disk and creating a virtual machine, I focused on having the virtual machine image that we can have here as a path. If we look inside the typical structure of the disk, here this disk is running, this one is running this virtual machine using this QuickCo QEMU disk. And when we will look at the terminal here, we will see that I've been using specific disk coordinates and space that are basically describing an image with 16 gigabytes used for the disk in this case, and then I converted it. We will see how for running it inside Kubevirt. So the base is always a quick call to disk for each virtual machine. Here I also have what I converted. This is the VMware Windows Server 2022 that I've been creating for this demo too, just using VMware Workstation. So instead of using libvirt, I could have been starting from there, but I wanted to show you that you can create VMware specific virtual machine. As you know, the resulting disk will be a VMX with VMDK bundle. You will have a disk split like I did in this case, but you can also do a single enormous disk and a VMX describing your virtual machine. Taking all of this and using the command line tool QEMU image converter, you will convert this disk to be a single QCO2 file, and we will see how we can import that disk in our current stack. Basically, before going to this command and explaining it, how it's done, that you can see here, I'm importing the QuickCo disk. I want to show also how the cluster is done. So the get node command is showing the 3 master nodes and the 2 worker nodes that I have in my cluster. And on top of this, I have a lot of pods, really a lot. I will show one by one, trying to describe how it's done, but really, you don't have to focus on the CNI. Here I'm using Calico. Rancher is installed. We will see the console is very useful for managing the cluster, but it's not really having an integration with Kubevirt. The container data importer is very important because at this service endpoint exposed by these pods, I will be able to upload my QCO disks and transform that in persistent volumes, and by the persistent volume claim, associating it to something that is the virtual machine resource created by the extension of Kubevirt. Then I have the typical components that you will have on your cluster, like the set manager, a fleet configuration installed by default by Rancher, the kube system with the components of the RKE2 cluster, what is remaining here from the Helm jobs that were configuring the RKE2 cluster, the ingress controller for Nginx to expose things, but I'm not really running on the cloud. We will see that I'm running the Metal Load Balancer for exposing services. And this is the real thing by Kubevirt. It's all here in a namespace so-called as Kubevirt, having the handler as a daemon set for each node to perform the activities that are required by moving the virtual machine across resources on top of the Kubernetes cluster. There is an operator that is controlling the reconciling for each kind of resource that you create, extending the Kubernetes API via Kubevirt, the API itself, because you can query that to start, stop, and manage virtual machines with a lot of commands, and the controller that will translate all the bundle and information coming out from the running resources to the operator and the controller manager inside Kubernetes. Then you have a local storage path that I'm not really using because I decided to include a complex storage system. And that is because you will be having resiliency for your disks and virtual machines. You will have replicas. You can configure snapshot backup recovery, a lot of features that will not be available in a normal storage class. So here, just think about Longhorn as a solution for complex storage system inside Kubernetes. It could be another solution like Rook operator for Ceph or Portworx or whatever other solution you want to use. It's easier for me that I'm using RKE2 and Rancher to integrate Longhorn. We will see why and how the console is briefly accessible. Here is the meta load balancer to expose services. In particular, I will expose the services from the running virtual machines to access some kind of resources that can be accessed. Then I install the monitoring cluster, but this is for another session and for eventually answering your question and answers. Like, yes, you can have a node exporter on each node of the cluster. You can monitor the virtual machines with the Kubevirt default Grafana dashboards that are available publicly in their repository. You can create your Promtail for logs and Loki system. I'm using the Grafana suite for this kind of thing, but it's the similar approach if you want to use Datadog, ELK, or whatever other solution that can be monitoring related to monitor each virtual machine. Tiger operator is for Calico, and finally, 2 namespaces hosting 1 Linux Ubuntu virtual machine that is up and running, a virtual machine running Windows that I decided to damage forcefully to show you how you can benefit from having this kind of persistent values also when incidents happen, like in example, you delete a persistent volume, but Kubernetes is preventing the termination of that volume. So you will be able basically to recover your contents without getting crazy. So again, virtual machines are created as a custom resource definition. Before going for the output of this command, I will come back to this document that I have here as a sort of notes and drafts that are also available in the GitHub repository as a set of recalls that you can use to create your own resources, or as an example that is really related to what is the rest of things that you can do. The virtual CTL image upload command for the PVC for this case is providing us the ability of creating the persistent volume claim for this that will be the persistent volume containing the disk for the virtual machine that we are going to create. You specify the storage class. For my case here, I've been creating 2 commands. One is this one with the default storage class that I've not been using. And then this is the example with the Longhorn storage class, just to show you how it's easy to target specific resources like storage classes from this virctl utility command that is basically just an abstraction, a command line of the kubectl virt crew command that you can install. It's already installed by default in the stack of Terraform, so it's available on those nodes that are running the cluster in the masters, in example. But for commodity and to be easy to manage for me, I decided to use the virctl command line, also because it supports additional things like the VNC ability as a subcommand to connect to the SPICE endpoints of the virtual machines and manage that via graphical interface if you install the graphical interface. Saying that, once you install the disk, you will have also the virtual machine CRD to provide to Kubernetes. This is a very basic version. I've been just using the naming of the machine, how many cores you use, the disk that is exactly that. You see here, the PVC that is referenced here as a name, it's then claimed here by the virtual machine and used as the disk of the resources. Here is the memory that I assigned to the virtual machine. This is really the base set of things that you have to know to run a virtual machine on top of the example stack that I'm providing here in the demo and available in the repository. You just have to define these two things, and the result will be that you will have a virtual machine namespace like this one running Ubuntu 24, AMD 64 architecture. It's running and true. We will access to it in a few seconds. It's namespace based. So if you imagine about the advantage in security terms for exposing resources, services, and whatever more, the namespacing is the first ability that you have inside Kubernetes to isolate segments of something. I decided to pair a virtual machine that is not running right now, but you can have it up and running. It's an ARM64, thanks to the ability of QEMU of emulating ARM, PPC, AMD64, and whatever. It will be slower because my machine, the nested virtualization cluster that I'm using, it's AMD64. It's a little bit more performance if you have that's up and running in an AMD64 architecture with virtual, not virtual, but bare metal real instances. And it's intended to be something like a digital twin virtual machine that you can have for a Raspberry Pi, in example, that you have as an edge device, and you want to use it as a virtual machine instead of having it up and running. And then the Windows machine that I created to show you that you can also import that source that was coming from VMware workstation or server, whatever is the MDK, converted and then imported as a virtual machine. Each virtual machine, when it's up and running, it is having a virtual machine instance or VMI that is another custom resource definition. When you can see where you can see that the IP managed by Calico is dynamic. You can also have specific static IPs in your network configuration for Kubernetes. But here, the nice thing is that you can use the service endpoint for each virtual machine, and you don't have to bother about network. Think about removing all the VLAN problems in designing virtual machines with your previous approach, the legacy one using vSphere, or also KVM and libvirt, focusing on having a network specific for running your resources and virtual machine. In Kubevirt, you don't have to bother about that. Here it's a sample of how I exposed the services of the virtual machine. And for this specific case of the demo, we are considering this Ubuntu 24 expose of the services in this namespace. You see here that I decided to expose a 6443 port. And this is because I installed inside this virtual machine another K3S Kubernetes distribution that we will be accessing from this command line, so from my physical machine, and an SSH that we will not use, but you can imagine not use the SSH because I'm going to create a session, graphical one, using the spice command, the spice component that is available inside QEMU KVM, the same that you will be using to access, in example, resources running on top of a cluster that is like this one. You just double click and you have the console for this machine that is the real master node. We are not using that now. We are using this command, and it's opening the Ubuntu pod virtualized or virtual machine that is running inside our cluster. Entering the password, it will open a session to this machine, to this Ubuntu virtual machine. And here we have just the terminal. I want to show you that I already installed distribution of K3s. So if I do a kubectl get nodes, I will see this K3s cluster that is running version 130.8. And this cluster, thanks to that service exposure that we have in the previous command that I showed you here, 6443, I'm also able to access that cluster using this pre-downloaded K3s Ubuntu 24.yaml and with this kubeconfig reference to see the nodes from my machine that is running that cluster. Running that cluster is also including that VMware, not VMware, but VMware converted Ubuntu image that is a virtual machine. And inside of that virtual machine, I have this service exposed that is the K3s running cluster where there are these resources that we can see they are the same available here in the kubectl get pods -a. They are exactly the same resources. Saying that, let's go to the console and what happens when I shut off the connection. It's almost obvious, but terminating the command on the command line will just leave the session untouched as it was. So keeping the persistent behavior of the virtual machine not affected by that command. You can also shut down the virtual machine from inside the virtual machine, and it will appear here in the list of the virtual machines as a stopped service. Saying all of that, we can go to show the brief Rancher console that we have from the installation. So you will be able in the demo to manage the Rancher cluster RKE2 using the console. So accessing to the resources, you will have a sort of graphical UI to see all the things that you are running. Workloads like pods, daemon sets, and whatever are also available here. You can manage that by a UI that is not that bad. You can also launch the command line and have the kubectl on top of the cluster. But the big advantage and takeaway is that you will have the Longhorn dashboard that you can call from the apps here or the Longhorn panel directly. It will open the same UI that I have here. It will give you a dashboard with a monitoring of the storage resources that you have here and per node. So the RKE2 cluster that we are using here are effectively configured to be managed by Longhorn to add volumes via the storage class. Here there are the volumes. You see that I have an healthy volume here with the Ubuntu 24. Then I have additional resources for monitoring. I imported the other versions like the launcher for the Windows Server 2022. I have it detached because I wanted to show what happens when you have a terminating session on the volume, unattended or wanted, until you really decide to remove this volume forcefully. Also removing the finalizers in Kubernetes, they will be there and the virtual machine will be starting like it is right now. But if you describe the pod that is running the virtual machine now, so let's say this one that is the container creating status pod, and you decide to describe this pod here to check the status, you see that it's failing on this persistent volume because this persistent volume is marked for deletion. But at the same time, you see that if I look at this, it is still bound to the persistent volume itself. And the persistent volume is marked as terminating, but it's still there indefinitely. Here you see the age is 32 days. So it's a lot of time that it's there. it's not damaged, and I can access eventually, in case of disaster recovery, this kind of resource manually or using the Longhorn console, creating a snapshot. So meanwhile it is detached, I can create a snapshot, a recurring job that is snapshotting or backing up the resources that are inside that volume. And that will be a big advantage because I will just have to restore it, change the reference inside what was the persistent volume claim for the virtual machine if I decide to re-import the volume again, changing the PVC, or if I want to use the same name, I will not have to perform additional changes here. I think that with all of this, I covered what I wanted to show you today, the ability of having everything inside Kubernetes running and scheduled by Kubernetes abilities to be a real orchestrator for each kind of workload that you can have for both your pods and cloud native applications like you run in Kubernetes generally, and for what is the VMware QEMU, KVM, virtual machine approach that you can have by Kubevirt on top of that, converting your legacy approach for the virtualization of the virtual machines. You don't have to bother about network. You don't have to bother about VLANs. Services are exposed the conventional way that you do in Kubernetes. And at the same time, if you want to configure a firewall bonus round, you just use the network policies of your favorite CNI. Here I'm using Calico, so my network policies will be the Calico network policies. I can do layer 7, so I can filter the application, the DNS thing. It's enormous, and it's just the starting point. So I look forward to seeing you checking out the repo, putting your stars on the repo, forking it, doing whatever you want, commenting, opening issues, and really follow up on this first chapter of a bigger conversation. Thank you for your attention. Ed, you can follow up with your conclusion, and it has been very nice to